Welcome back to Calculus by Ansari. In this video, we're going to be talking about why limits are useful in calculus and why can't we just define a function and just evaluate the function at given values. So let's discuss this. I'm going to define some function. I'm just going to draw the graph for it, and I'll just call the function g of x. So this is the xy coordinate system, and then I'm going to draw the function to be something like this. And this might look familiar. It might be, it might look to you that it's the f of x equals x to the third. But I'm going to define to be, actually let me redraw it. I'm going to define a hole somewhere. So it should look something like this, and there's some hole right there, and then it just keeps going up like that. And I'm just going to say that this function is g of x. Again, we don't have the equation for it, but we do have the graph. Okay, now let's say this point right here is 3, and the corresponding y value, I don't know, we'll just say 27. So right here is a hole. And what this hole means is that this function, g of x, is not continuous at this point. And what that means is that this function is not defined at that particular point. And it looks like the function is defined everywhere else because on here we can see that it is defined, and also the arrows just point towards infinity, and that just also means it's defined elsewhere. Now, so we cannot say that we cannot say in this case that g of 3 is equal to 27 because it is not. G of 3, again, this is a g of x, right? So this is g of 3 would be this corresponding point right here, but we cannot say g of 3 is equal to 27. It's actually not equal to 27 because g of 3 is not defined, right? In this case, this function does not define g of 3 for us. However, we can define g of 3 with limits, and this is where limits become pretty useful. For discontinuous functions, we can still explain what's happening to the function around that point because it's a pretty it's a pretty symmetric thing that's going on. It's just one little point that it's not defined at. Everything else is looks continuous, and it nicely just attaches afterwards. So we can define this function with a limit, and we can say that the limit as x, again, this is how we read this, the limit as x goes to 3 of g of x. Again, we don't write the of and those English words, but this notation denotes that. So the limit as x goes to 3 of g of x is equal to, well, it's equal to 27. Because as we approach 3 from both this side and this side, we approach, the function approaches 27. Again, what I mean by the function approaches 27 is the y-coordinate of the function approaches 27. So we can say that limit as x goes to 3 of g of x is equal to 27. And this right here is what a limit is one way a limit is easily utilized. Now, let's say we have, so I'm going to erase this. Let's define one more graph. Let's say we have the graph. Actually, this time let's define a function. I'm going to define f of x is equal to, okay, we'll make the function a little bit weird. I'm going to say x over x. X over x, you might say this is just 1, and it is, but we can't quite set it equal to 1 in this case because there's a domain issue. And what I mean by that, this is equal to 1 at every point, except at x equals 0. At x equals 0, this is not defined because we cannot say f of 0 is equal to 0 over 0. I mean, we could, but this is not defined, right? So for that reason, this function needs to just stay as x over x, which we know is just 1, but we need to make sure that when we graph it, we leave a hole for when x is equal to 0. And if that's confusing, let me show you what I mean by that on the graph. So we have a y-coordinate, or sorry, y-axis, and our x-axis, x-axis, y-axis, and again, we can just think of this as f of x equals 1. So how do we graph f of x equals 1? Well, that just means y is 1 at every point, right? So this is y is equal to 1. Oh, oops. And we can just draw a straight line. Here, let me do a different color through that. So something like that. But we have to be careful because we defined the domain earlier. We said at x equals 0, this function is not defined. So there's a hole here, and I'm just gonna represent the hole with, I'm gonna draw a little circle around it. So actually here, let's just split up the line so we can make clear that there's a hole there. So like that, and then like that, boom. And then we'll make it clear that there's a hole, draw a little circle. So again, this is f of x equals 1, except, or sorry, if f of x equals x over x, which is f of x equals 1, except there's a domain issue at x equals 0. So we cannot say that f of 0 exists. F of 0 does not equal 1 in this case. However, the limit as x goes to 0 of f of x, which is just x over x, is equal to 1. And again, we defined the function at that point that the function did not define with limits. We said as it approaches 0, it is equal to 1.